All right, so what we're going to be doing today, we're going to use whatever we learned so far. We learned how to just manipulate a bunch of like complex numbers. So we're going to basically use whatever we learned and say, how can we apply that to a circuit, right? We already talked about like phasors. We said like if you have a circuit that has like AC source that is a sine wave, we can always write that sine wave in terms of a phasor, right? So let me quickly remind you of what we had. So assuming we have like a circuit, and this circuit is connected to, let's just say some source, right? And let's just call this source VT. Let's just say this VT is some magnitude Vm times e to the I omega t plus theta v, right? By that, I mean I have a sine wave as my source, right? Do you agree this is a sine wave? Yes? Remember, like e to the I whatever is always like a cosine of that whatever plus I sine of that whatever, right? So this is indeed a sine wave, right? So we can always represent this in terms of a phasor. Let's just show that phasor by capital V. And all we need is to have this magnitude Vm and the phase theta V. And we know this is happening at frequency omega. And this is the angular frequency, not the regular frequency that we're familiar with. Right? Right? Hopefully it stays this way. Right? So all I care about is the magnitude and the phase. And we call that the phasor representation. So a phasor is a complex number that represents the magnitude and the phase of a sine wave. Right? We also said just because the circuits that we're dealing with, they're all linear circuits. So if my sources are sine waves, everything else in the circuit must be sine wave, and that are happening at the exact same frequency. The only thing that changes is the magnitude and the phase. So if I wanted to find, like, for example, something else, like voltage across like a resistance, current through like a capacitor, or like whatever I wanted to find, it is still a sine wave, which is happening at the exact same frequency omega. The only thing that changes is the magnitude and phase. So this phasor representation is more than enough for us, right? Let me quickly remind you. Reminder. Since the circuit is linear, assuming the sources are sine wave at frequency omega, all currents and voltages in the circuit are also sine wave at frequency omega, but we have different magnitudes and phases. So if we're able to determine like what the magnitude and the phase is, we're done, right? We know exactly like what that voltage or what that current is, right? So let's look at this from like another angle. So if I have my circuit, this is Vt, which is Vm e to the I omega t plus some theta v. If I want to find some current IT is Im e to the I, again, omega t plus theta I, right? So this magnitude and this phase, I got to determine, but this is exactly the same as this, right? So here's the thing. If I can find the relationship between all the elements, between like I and V for all the elements that we learn, and if it can come up with like something that's very nice, like Ohm's law and frequency and domain, then our lives would be like much, much easier. Why? Because I can take my circuit from time domain, which I know the relationship between like V and I is not necessarily like Ohm's law. For example, if I have a capacitor, the relationship between I and V is I equals C dV dt. So it's not exactly like Ohm's law. But if I can find like a relationship between like I and V for a capacitor that looks like Ohm's law in frequency domain, then that's pretty good. Because I can take my circuit from time domain to the frequency domain, right? And I can treat all the elements that I have as a resistance and apply whatever I learned up to this point, Thevenin, Norton, mesh analysis, all those, to the circuit in the frequency domain. And since there's always a unique relationship between time domain and the frequency domain, if I solve the circuit in the frequency domain, I can convert it back to time domain, and I have the solution. The question is there such relationship? Let's figure out. Let's look at the first element that we're all like familiar with, resistance. So case one, phasor relationship for the resistor. Let's just say I have like the circuit that's connected to some resistor with value R. Let's just say current through it is IT, voltage across it is VT, right? And let's just assume current through this resistance is indeed a sine wave, right? So I of t, let's just assume it is Im e to the I omega t plus theta I, right? Since it's a sine wave, I know exactly like what the phasor representation of this I is, right? What is the phasor representation? Let's just show it with capital I. All I need to know is the magnitude Im and the phase theta I, right? So that is my phasor representation of the current. What is Vt? We know that. We've been using it. What is it? Vt is R times It. It's Ohm's law, right? So I know Vt is R times It. If I plug this It in here, what do I get? I get R times Im e to the I omega t plus theta I, right? What is this telling me? What it tells me is that the voltage across a resistance is still going to have like the sine wave form. It is happening at frequency omega. The phase of voltage across the resistance is exactly the same as phase for the current through it. So they're in sync, they're in phase. The only thing that changes is the magnitude of this Vt, which is R times the magnitude of I. Right? But do you agree Let me quickly write down the phasor representation of this V. The phasor representation of this V is some Vm, which is the magnitude of V, and theta V. Right? It's a phasor representation. If I compare this to this, what is Vm? It's Rim. What is phase of Vm? That's just theta I. So they're actually the same. So this tells me Vm is R times Im, and phase of V is exactly the same as phase of I. Should we call them like in phase, in sync? Exactly the same, all those names. Right? But look what's happening over here. Do you agree this can be written in terms of phasor representation of I? It can, right? R is a constant, so I have R times phasor representation of I. That should be the phasor representation of V. So what I have over here is that V equals R times I, and this V is the phasor representation of Vt, and this I is the phasor representation of It. Right? You with me so far? So far, if I have a resistance, I could establish the Ohm's law in the frequency domain. And what this equation tells me is that the relationship between V and I is through this R, even in frequency domain. So if I take resistance from time domain to the frequency domain, the value of R remains unchanged. Right? Let me quickly plot Vt and It. We know exactly how they actually relate to each other. So if I plot it, this is T. And if this is my It, for example, I know Vt is exactly the same as It in terms of phase. The only thing that changes is the magnitude. Right? So my Vt must look like this. Right? And this is my Vt. So the phase of Vt and It are exactly the same. The only difference is the magnitude here. Right? It could be like bigger or like a smaller depending on R, but pictorially it looks like this. Right? They're happening at the exact same phases. Right? So this is pretty good. So this is pretty good. So we don't have like any issues with R. Let's move on to the inductor and try to establish the same relationship for an inductor. So case 2. Phasor relationship for an inductor. So let's just say I have this circuit. I have an inductor L with current through IT, voltage across VT. Right? Let's again assume IT is some Im e to the I omega t plus theta I. Right? Which I know the phasor representation of this IT is I, that has Im with the phase theta I. What is the relationship between V and I for an inductor in time domain? V is L di dt. So it's through derivative. So I know Vt must be L di dt. So I have to take derivative of this it, right? So I have L times Im. What is the derivative of E I omega t plus theta I with respect to t? Well, I have to take the derivative of the exponent in terms, like with respect to t, and then multiply it by the same exponential. What is the derivative of e to the I omega? What is the derivative of the exponent with respect to t? It's just like I omega, right? Because I theta I is just a constant, right? So that would be I omega times e to the I omega t plus theta I. Right? Let's look at the phasor representation of this V. This phasor representation, again, that must be some Vm and the phase theta V. Right? What is this Vm? This Vm is the magnitude of this Vt. Right? What is the magnitude of this Vt? The magnitude of L Im I omega e to the I omega t plus theta I. That is Vm. Right? If I want to find magnitude of a multiplication, what is that magnitude? It's a magnitude of each of them. So what is the magnitude of L? Well, as L is a real number, so the magnitude of L is exactly L. What is the magnitude of Im? Same thing. Im is a real number, so the magnitude is still Im. What is the magnitude of I omega? Magnitude of I omega is magnitude of I times magnitude of omega. What is magnitude of I? 1. Keep that in mind. Reminder. E to the I phi, if I look at the magnitude of it, that is the magnitude of cosine phi plus I sine phi. What is the magnitude of this? This magnitude is square root of cosine squared phi plus sine squared phi. What is cosine squared of apple plus sine squared of apple? 1, always 1. It doesn't matter like what this phi is. So that's 1. Do you agree I, the imaginary number I, is a special case of this when phi is pi over 2? Right? So absolute value of I is absolute value of e to the I pi over 2. There's always 1. Yes.
For that, did you write absolute value of cos phi plus I sine phi?
No. Oh, this one? Yes. Yes. So what is the absolute value of I omega? Omega then, right? So it's omega. What is absolute value of e to the power of I whatever? What is it? 1. We just set it down here. So this is this Vm. This is the magnitude of this V. How about theta V? If I multiply a few complex numbers, what happens to the angles? I have to add them, right? So what is the angle for L? L is a real number. There is no angle for it. So the angle is 0. What is the angle for Im? Still 0 because it's a real number. What is the angle for I? Remember, it's happening at 90 degrees. So the angle for I is, again, remember I can write it as e to the I pi over 2. And this is the angle. So the angle is pi over 2, right? Plus, what is the angle for omega? Again, it's 0. What is the angle for this e to the I omega t? Well, remember, this is due to the I. So the angle is like just theta I, right? So it's pi over 2 plus theta I, right? Right? What does that tell me? That tells me if I look at v of t and compare it to I of t, the magnitude will be stretched by this number. But the phase of v of t is phase of I plus pi over 2, which means if I plot it, I'm going to see v of t first and then I of t, which means v of t is leading I of t by pi over 2. Okay, so let me quickly draw it. This is t. If this is my I of t, again, remember this I of t is periodic, right? This would be my v of t, right? So v of t leads I of t by pi over 2. If v of t is leading I of t, it means I of t is lagging v of t, right? So another way of saying it is that like I of t lags v of t by pi over 2, right? Right? But look, let me rewrite this vt. Vt is L times I omega times Im e to the I omega t plus theta I, right? Do you agree I can replace this by the phasor representation of I, right? If I take it from time domain to the frequency domain, this can be replaced by the phasor representation. I can replace this by its phasor representation as well, but the coefficient over here is going to be I omega L. So if I go from time domain to the frequency domain, this is going to be the relationship. And this is the phasor representation of Vt. And this is a phasor representation of It. Again, everything holds, right? Because this has like that Im in it. So if I want to look at like the magnitude of this V is going to be omega L times Im, right? And if I want to look at the phase of it, it has like the phase of I in here, and I have like pi over 2 over here. So everything checks out, right? But what happened over here is that I was able to get something very similar to Ohm's law again. The main difference here is that like if I look at this coefficient over here, this coefficient is complex, right? But again, that is pretty good because I was able to get something very similar to Ohm's law. So what it tells me is that if I go from time domain to the frequency domain, if I have an inductor with value L, if I go from time to the frequency, I have to change the value of omega L by I omega L, and then I can treat it just like a resistor because I have the relationship between V and I as Ohm's law. That's beautiful, right? If we can establish the same relationship for the capacitor, we're done, right? We can take all the elements from time domain to the frequency domain. We can take our sources from time domain to the frequency domain. And we can solve the circuit in frequency domain and then convert it back to time domain. The only catch here is that if this is happening, I have to deal with like complex numbers. right? So let's just see if we can actually establish the same relationship for the capacitor. So case 3. Phasor relationship for a capacitor. Again, let's just assume I have a capacitor. Let's just say current through it is IT, voltage across it is VT, the value of capacitor is C. Right? This time, let's just assume V of t is a sine wave. Doesn't matter, right? Because if one of them is sine wave, the other one must be sine wave as well. So let's assume like my voltage is sine wave. So let's just say V of t is some Vm e to the I omega t plus theta v. Right? You with me so far? What is the phasor representation of this? Well, V is this magnitude, Vm, and the phase theta v. Right? Right? What is the relationship between V and I for a capacitor? I equals C dV dt. So let's write it down. I of t is C dVt dt. So if I wanted to compute this, what do I need to do? I need to take derivative of this. So I have C times Vm. What is the derivative of this exponential? Again, I have the derivative of the exponent, which is I omega, times e to the I omega t plus theta. Right? Right? Again, I can write this as I, which is some magnitude, and base of I. Right? What is the magnitude of I? What is Im? Remember, Im is the magnitude of C Vm I omega e to the I omega t plus theta v. Right? I have a bunch of like complex numbers, in general complex numbers, multiply. To find the magnitude of the multiplication, I have to multiply each magnitude. What is the magnitude of C? Well, it's a real number, so the magnitude is the same. So it is C. What is the magnitude of Vm? Well, again, it's a real number, so it stays the same. What is the magnitude of I omega? That's just omega. Remember, magnitude of I is 1. Right? So that's omega. What is the magnitude of e to the power of I omega t plus theta v? 1. So that is basically Im. We're done. What is the phase of I? Again, I have to find the phase of this expression, right? Keep that in mind. I'm going to write it down over here. If A is in R, phase of A is 0. Right? Let me quickly remind you this. If I have I, phase for I is pi over 2, because I can write I as e to the I pi over 2. Right? Right? So what is the phase here? What is the phase of C? What is it? C is a real number. So what is the phase? 0. What is the phase of Vm? Still 0. What is the phase of I omega? It's just the phase of I. So it's pi over 2. So it's pi over 2. What is the phase of like e to the I omega t plus theta v? It's just theta v. Right? What is this telling me? What it tells me is that if I look at the current through capacitor, this time current through capacitor is leading its voltage by pi over 2. And if I want to know the magnitude and see how I stretch my magnitude, this is basically how I stretch my magnitude. By C Vm times omega. What's very, very important is that this number over here actually depends on the frequency of the circuit that we have. Right? So let me quickly draw this. So if this is my V of t, this time I of t is leading. So I of t leads V of t by pi over 2. Equivalently, V of t is lagging I of t by pi over 2. Right? Yes.
Did you say that E of T leads I of T, or that just mean?
That just mean lagging, right? Yeah. Right. So let me quickly write down that I we have. So I know I of t is C I omega Vm e to the I omega t plus theta. Right? Right? Do you agree I can replace this by the phasor representation V? I can replace this I by its phasor representation I. But this time, this is going to be my coefficient. Right? So I have this relationship. I equals I omega c times V. Obviously, I can find the VI relationship, and V equals 1 over I omega c times I. Look what happened. Again, I was able to find Ohm's law-like relationships. So if I have a capacitor, I can change the value of the capacitor by 1 over I omega c in the frequency domain, and then treat it just like a resistance, because I have like a relationship between V and I that follows Ohm's law. Right? Again, remember, this number is complex. And it's being controlled by frequency of the circuit. Right? So in general, we can say, if I go from time domain to the frequency domain, I still have like something that's very similar to Ohm's law. Right? So let's make that point then. Remark? Any steady state analysis or phasor analysis of a circuit with sine waves as source can be done using Ohm's law. So we know V equals some complex number Z times I. Right? And if I have a resistance, this Z is R, which is a real number. If I have an inductor, this Z is I omega L. If I have a capacitor, this Z is 1 over I omega C. Right? We call this Z impedance. So we call this Z impedance. Right? In general, this impedance is a complex number. So 0.1, in general, Z is a complex number. Right? Also, we know in general, this Z depends on omega, depends on the frequency of the circuit. So 0.2, in general, Z depends on omega, which is 2 pi f. Right? Great question. Is impedance a phasor? Is it? Absolutely not. An impedance is just a complex number. But a phasor represents a sine wave. Right? So impedance is not a phasor. Impedance is just a complex number. 0.3. Impedance is not a phasor. Why? We just explained why. Right? What else can we say about like this impedance? Yes.
What is 2 pi f? What
It
is
means
f?
frequency.
Oh, okay.
Yes. What else can we say about phasors, impedance? Remember, the relationship between V and I is through Ohm's law, right? So if I have like a bunch of them in series, I can combine them and get one impedance. If I have a bunch of them in parallel, I can combine them and I can get one equivalent impedance, right? So 0.3, 0.4. V equals ZI allows us to use the same methods as we had before for resistive circuits. We only need to convert the circuit to the frequency domain version. How do we convert a circuit to the frequency domain version? Again, remember, if I have a resistance, I'll replace the value by the exact same value. If I have a capacitor, I change the value of the capacitor to the frequency domain. It's 1 over I omega C. If I have an inductor, I'm going to change the value to I omega L. And as soon as I have like all these values, right, I have a bunch of like resistors in frequency domain. So let me quickly summarize like this over here before I talk about like some other things. So let's just say I have this element in time, element VI relationship in time, element in frequency domain, VI relationship, and some notes about like the phase. Right? So the very first thing I have is just a resistor. Just show it by this. R. I know the relationship between V and I as Vt equals R times It. Right? We can take the element to the frequency domain. The value remains unchanged. And I know the phasor relationship as V equals Ri. And we know it is in phase. Which means the phase of V is the exact same as phase of I. Right? So that is pretty nice. If I have an inductor, with value L, right? I know Vt is L dit dt, but I can convert this to a frequency domain version of it. I have to replace the value by I omega L. I know the phasor relationship is V equals I omega L times I. And we know V leads I by pi over 2, or 90 degrees. Right? The last element we have is just a capacitor. Let's just say it has the value of C. I know I of t is C dVt dt. I can replace this capacitor with the frequency version of it. I have to change the value though. The value is 1 over I omega C. And I know the relationship between V and I is V equals 1 over I omega C times I. And in this case, I leads V by pi over 2. Right? In all the cases, this is my Z. In this case, this is my Z. And in this case, this is my Z. Right? So in general, we have this very nice relationship that V equals Zi. Right? And given that we can actually like combine things, right? So if I have connections, if I have Z1, Z2 all the way to Zn, I can replace this by one equivalent impedance. Let's just call it Zt. And I know Zt is the summation of all Zi's, I from 1 to n. So that's a series connection. And if I have like a parallel connection, let's just say I have Z1 in parallel with Z2 all the way to Zn. Again, we're going to treat it exactly as a resistor. So to find this Zt, we're going to have to use this formula. Sigma I from 1 to n, 1 over Zi. Right? So the bottom line here is that as soon as I go from time domain to the frequency domain, I can treat all my elements as a resistor, right? If you guys recall, when we're talking about like RLC circuits, for example, I said if I have R, L, and C, I cannot combine them. So I had to write the differential equation to be able to solve it. But since I have a sine wave as my source, I can go from time domain to the frequency domain. And as soon as I go from time domain to frequency domain, I change the values to its corresponding values. I can treat them all as like a resistor, and I can just add them all up. Or find the connections, whatever the connections are. Right? So it makes our lives like much, much easier. So I can basically go from time domain to the frequency domain. I can solve whatever I want, find a solution in frequency domain. There is a unique relationship between the time domain and the frequency domain. So I can come back to the time domain and I know the solution. So it's like pretty cool. It's like very easy and it's very cool. Let me quickly make a remark about this impedance. If you guys recall, when we had like a resistive circuit, we said we can always find like the total resistance by looking at the voltage across it and divided by current through it. Right? Same thing can happen over here as well, because we have like something similar to like Ohm's law. So, remark, if I have a circuit, and let's just say this is connected to some voltage source with Vm times theta V. And let's just say I find current through it, and the current through it is Im theta I. I can find the equivalent impedance, right? By dividing this V by I, right? Something that we did before, especially we did it a lot when we had like Thevenin and Norton equivalent circuits. So I know the Z equivalent is V divided by I. And again, remember, we have this nice relationship only in frequency domain. So if I have like sources, I have to like take it to the frequency domain. And that's exactly what I did. Like my sources and the current that I found, they both are in frequency domain. Right? So I know I have like this relationship. But what is V? This V is Vm with phase theta V. This I is this Im with phase theta I. If I divide two complex numbers, what am I doing essentially? What I'm doing is that I'm dividing my magnitudes and I'm subtracting the angles. So this division over here is basically Vm over Im, but the phase is theta V minus theta I. Right? And remember, this was the same way as this. Vm over Im e to the I theta V minus theta I. Remember that? We said like these two are equivalent like representations. So if I have this, I know the Cartesian representation as well. Right? So what is the Cartesian representation? It's Vm over Im cosine theta V minus theta I plus Vm, well, I times Vm over Im sine theta V minus theta I. Right? So this is my real part. So let's just call it R as a function of omega. Now let's call this portion the imaginary part. We call it by x of omega. right? So this is basically R omega plus I x of omega. The real part of this impedance is called resistance. The imaginary part of it is called reactance. Just keep that in mind. Remember, Z is always a complex number, right? So now we have like all these. We got to be able to solve any circuit that we want, right? So let me quickly give you a recipe as to how we can apply this to any circuit. So AC steady state analysis of a circuit. The first step is we're going to convert the time domain signal, time domain circuit, to frequency domain circuit. So convert the circuit from time domain to frequency domain. Again, remember, when we're converting the circuit from time domain to frequency domain, we're converting everything, including the sources, right? So for the sources, we're going to replace the sources by the phasor representation. For the resistance, we're going to change it with the value of the resistance because it remains unchanged. For the inductor, we're going to change the value by I omega L. Remember, omega is given to you. And we're going to change the value of C by 1 over I omega C. So we use phasor representation of sources in frequency domain. For elements, if this is time domain and this is frequency domain, if I have a resistance, this value remains unchanged. If I have an inductor in time domain, the value in frequency domain becomes I omega L. If I have a capacitor, this value becomes 1 over I omega C. Right? Second step, use your favorite method in frequency domain and solve for unknown. What do I mean by your favorite method? KVL, KCL, mesh analysis, I don't know, node analysis, Thevenin, Norton, whatever we talked about. Superposition, all of them. So basically, KVL, KCL, mesh nodal analysis, current voltage divider. What else do we have? Superposition, Thevenin, Norton, source transformation, all of it. All those hold true because as soon as we go to the frequency domain, everything is a resistance. right? It's a complex valued resistance, nonetheless, it's a resistance, right? Up to this point, when I solve for whatever I want, I have the solution in frequency domain. What do I need to do? I have to convert it back to the time domain. Step 3, convert the solution back to time domain. That's it. Let's do a few examples to see how we can apply this. Okay. Any question about these before I move on to like an example? Is that clear what we're trying to do? Is that clear why we're going from like time domain to the frequency domain?
You say time domain is rectangular and then frequency domain is
No. Time domain is something that changes over time. So your variable is time. Frequency domain is another domain, completely like other domain, where your variable is frequency, right? And as soon as you go from time domain to the frequency domain, despite the fact that your time domain signal is a real valued function, your frequency version of the signal is going to be complex. So you're going to have to deal with like complex numbers. So in time domain, everything is real. But as soon as you go from time domain to the frequency domain, everything becomes complex. Right? Any other question? So let's do an example. Let's just say I'm given this circuit. This is V of t equals 120 sine 377t plus 60 degrees. I have a capacitor with value 50 microfarad. I have a 20 ohms resistance, followed by an inductor with value 40 millihenry. Right? And the question is asking me, what is this IT? Right? Again, one way to solve for this is just write down the differential equation. Right? We know how to write down the differential equation. We just basically need to write a KCL on the top node and then write down the differential equation. That's not difficult. Right? But I guarantee it's like much more difficult than converting this to the frequency domain, solving in the frequency domain, and convert it back to time. So let's use this method then. Let's redraw the circuit in the frequency domain and just solve it. Yes?
377t plus 60.
377t plus 60 degrees. Yes. All right. So let's draw this in frequency domain. How do I draw a circuit in frequency domain? It's the same exact same circuit. The only thing that changes is like the values. If I have sources, I have to replace the sources by the phasor representation. Right? So my circuit is exactly the same. Now I got to determine like what these values are. First of all, what is my omega? Omega is 377, right? The source over here dictates what frequency I'm working in. Right? Do you agree that omega over here is 377? So that's radian per second. Right? What is the phasor representation of this VT? Remember, all I need is just the magnitude and the phase. So what is the magnitude? 120. So this is like 120. What is the phase? What is the phase?
Oh, 60.
It's 60 minus 90. Why? Because I have a sine wave. So reminder, if x of t is some xm cosine omega t plus theta, the phasor representation x is xm with the phase theta. If x of t is xm sine omega t plus theta, the phasor representation x is xm theta minus 90 degrees. So what is it over here then? That's 60 minus 90, which is like 120 with negative 30. Yes? We're good? What is the phasor representation of this R? It remains unchanged. So if over here it's 20, down here is still 20. What is the phasor representation of L? It's I omega L. So it's I times omega times L. Right? What is the phasor representation of this capacitor? It's 1 over I omega C. So it's 1 over I times 377 times C, which is 50 microfarad. Right? I'll point something out really quickly before I solve this. If I have a capacitor, we said we're going to replace this capacitor by 1 over I omega C. Right? Do you agree I can write 1 over I omega C as negative I over omega C? Yes or no? I can, right? I can get rid of this like I over here by multiplying this I by its complex conjugate, which is negative I, right? So I'm going to have negative I on the top. I have negative I times I, so it's negative I squared, so it's 1. So it's 1 times omega C on the bottom. And on the numerator, I have minus I. Keep that in mind, right? Because if I look at this, having this I down here can be a little like difficult to work with. But if I use this representation, now I have my complex numbers on the top, so it's like much easier to work with, right? All right. What do I have over here? Do you agree these two are in series? Are they? If it is in series, what is the equivalent? Basically like this 20 plus I times 377 times 40 million. Right? Yes? They're in series, so I have to add them up. Do you agree these two are in parallel? They are. They have the exact same head and tail. So I have negative I over 377 times 50 microfarad in parallel with 20 plus I times 377 times 40 million. Right? Again, this is not very difficult. We did same things before, right? Last lecture, we actually did something very similar to this, right? If I call this Z1, if I call this Z2, Z equivalent is Z1, Z2 divided by Z1 plus Z2. Right? It's exactly the same as what we had before. Right? It turns out this is gonna be some A plus IB. We can find A and B, right? Just by writing down this formula. But we can write it in terms of the polar form, which is 30.95 with angle 9.3. Right? As soon as I get to this point, I can convert it to the polar form. You agree with me? How do I do this? How do I go from A plus IB to this form? Basically, if I call this R, if I call this theta, how do I get R and theta? Remember, R is square root of A squared plus B squared. Theta is tangent inverse of B over A. Right? So I can easily get that. I can give it to my calculator and it spits out that number. The only thing I need to make sure of is that I know exactly in what quadrant this A plus IB is located to get the right angle. Right? It turns out this is basically the simplification. So what do I have? Let's call this V. This is I. So what I end up getting is a circuit that looks like this. V equals 120 minus 30. This is my Z equivalent, which I know it is 30.95 with angle 9.3 degrees. What is I? I is V divided by Z equivalent. Remember, I have this V equals ZI in frequency domain. Right? So I have 120 with angle minus 30 divided by 30.95 with angle 9.3. When I divide two complex numbers, what do? I divide the magnitudes, I subtract the angles. Right? So I have 120 divided by 30.95, angle minus 30 minus 9.3. This is 3.88 with the angle minus 39.3. Right? We're not done yet. We know I in the frequency domain. What is I in time domain? What is IFT? Yeah, exactly. It is 3.88 cosine omega t plus the angle. What is omega? It's 377, right? Omega does not change. So that is IFT. Right? Again, you can check this, you can verify this by writing down the differential equation. Okay? Any question? Is that clear how we do this? Again, as soon as I go from time domain to the frequency domain, everything acts as a resistance. And we're good. We know how to solve them. Let me quickly remind you of something, because that's something that we use a lot. So I want to make sure that we all know what it is. Reminder. If I multiply two complex numbers, right? Let's just say Z1 is R1 e to the I theta. Z2 is R2 e to the I theta 2. When I'm multiplying two complex numbers, I'm multiplying the magnitudes and I'm adding the phases, right? When I'm dividing two complex numbers, what I'm basically doing is that I'm dividing the magnitudes but I'm subtracting the phases. Right? That's very, very important. Right? Adding them up, if I have it in terms of polar representation, it is a little difficult to add these two things. So I have to convert it back to the Cartesian form, and I can add them. Right? But for multiplication and division, this polar form is the easier way. Right? So what we're going to be doing like next lecture, we're going to continue on this. We're going to do a few more examples. But essentially, that's what it is. We go from time domain to the frequency domain. We have everything replaced by its equivalent. We solve the circuit in frequency domain, convert it back to time. All right? I'll see you guys Monday.